I will try to go through a variety of social science modeling platforms and tools for complexity research in about 15 minutes. So it's going to be, of necessity, a brief presentation. And let me just say, I'm actually at George Mason University. There are three universities named George in Washington, D.C. Georgetown, George Mason, and George Washington, and it's confusing. All named after different Georges, by the way. Okay, so I'm an age-based modeling specialist. We've seen lots of network things yesterday. I won't go into networks, although I'll make some comments about networks at the end. So let me just mention, and I'll start out by saying that today, in this 2015 era, we're going through a revolution in the social sciences, in particular in economics, and in three broad categories. The origins of the reasons for those for the revolution is that we can do experiments today. We couldn't do that 20 years ago. When I was a graduate student, experiments were just on the horizon. Vernon Smith won the Nobel Prize over 2000X. I think it's 2002, maybe 2003. He shared it with Kahneman from the film, so whatever it said for Kahneman. We can do large-scale computing today in economics. We couldn't do that before. I'll show examples of that today. I've written here, since there are many physicists in the audience, there's a funny quip in the Mitch Waldrop book about complexity, where the late Gottfried Meyercrest walks into Brian Arthur's office and says, "You know, Brian, Professor Arthur, just give me the equations for the economy, and then I'll program up you a model of the whole economy." And of course, there are no equations for the economy. That's the whole point. And so we need to take a different framework if we're going to make progress in the social sciences. And then the last thing I'll mention is big data. And today we have a variety of ways in which we can use big data, and that'll become clear as I go through these slides. Now this is a PowerPoint version of a keynote talk. This very busy graph was supposed to unfold column by column, so I'm going to apologize ahead of time that it doesn't look the way I hoped it would. But basically, look at the things on the left-hand side. These are all things that we have in our models. We have firms, we have agents interacting. The agents have beliefs and aspirations and goals and et cetera. Now, the way that I learned to model those things on the left, when I was in graduate school 20 years ago, was to do the stuff in the middle, which is this, I've written here, the simplistic versions. Okay, so how many agents do we use? Well, we use one agent if it's decision theory, two if it's game theory, and we use infinite number if we're going to model some macro system, because we don't know how to model 100 million or something, right? So these are the ones that are mathematically tractable. How do we specify agent behavior? We give agents a scalar valued utility function that's fixed. It does not change over time. How do we model agent interactions? Well, those are well mixed. How do we model the markets? Markets are, WMAD stands for Walrasian, Mackenzie, Arrow, DeBrew models. We saw a picture of Ken Arrow yesterday. There's one global price vector that clears all markets. We typically don't model institutions in general equilibrium. We don't, the OECD doesn't exist in the Walrasian picture, right? That's one extreme way to put it. What is a temporal structure? It could be static, it could be one shot, as in game theory. Or in modern macro, we say, well, the whole thing is in equilibrium. We just do impulse testing on the whole thing. Who governs the graduate school economy? It's a benevolent social planner who maximizes welfare for everybody. I mean, so everything in the middle, I wanted to make it, I've written in a stylized way perhaps, but it's meant to be extreme as an example of how the stuff on the left-hand side is really dealt with in a very simplistic way. So I could have written simple. I wrote simplistic, meaning it's too simple, and as opposed to realistic. Now I was going to call it complexity theoretic, but I just call it realistic. What would a good model really have? A good model would have the real number of participants in the economy who are there. If it's a financial market with 5,321 traders, let's put them all in there. Those people have heterogeneous information. They interact in a network. Their behavior is something much richer than rational. There's multiple levels to real social systems. There's the agent level, there's the social level. And agents interact in asynchronous ways, and they're dynamic. Governance is not done from the top down by a social planner. It emerges from the bottom up. And if Roland is still here, I put the last bullet for Roland and his co-author. Policy. In the model of policy that I learned in graduate school, we design policies from the top down. I worked at Brookings for 15 years, and we tried hard to design policies from the top down. But in reality, policies evolve, and they emerge from the bottom up. The point of this slide is simply to say, we would like to do the stuff on the right. We do the stuff in the middle. Why? We'd like to move from the middle to the right, but we can't because why? Because it's too hard. Mathematically, no one knows how to relax all those middle things. All the things in the middle are done for mathematical convenience, to be honest. I mean, Ken Arrow was a mathematical economist. My training was as a mathematical economist. We don't know how to relax all the stuff in the middle to go to the stuff on the right. This is, some of you will know that Jim March was a colleague of Herb Simons back in the 60s, former dean of the Stanford Business School. So what are we going to do? We need to have a solution. I'm going to argue that agent computing is a solution in which we populate a computer with a large number of software objects that have beliefs, preferences, desires, etc., and we let them interact. Now, the trouble with this technology is that it's very, very general. I mean, arbitrary numbers of agents with arbitrary beliefs doing arbitrary numbers of things for arbitrary amounts of time, an arbitrary network. I mean, this could be anything, right? This is not a strong constraint on what can happen. So as opposed to the math econ paradigm where we drop the keys somewhere over in the corner, but we're looking for the answer under the light bulb, the trouble with the agent paradigm is that we have this incredibly sophisticated, I'll say just incredibly powerful tool, and we're all children on how to use it. Okay, I'm going to argue that basically we don't know how to use the tool today. It's very powerful. Okay, so here's the story. If you try to relax everything at once, you're like Christopher Columbus taking off, trying to find India. And you land somewhere, and where are you? You call it India, but you're not India. It's somewhere else. You don't know where you are. So you take off, and you see land ho. This is like us saying, well, agents make economies. So somebody can gin up, everybody who can program can gin up their own agent-based model of an economy. And the trouble is, most of those economies are of no interest because they're not relevant to our modern economy. So this very powerful tool, I've written here in the title, our agent models need to be disciplined with data. That is, for example, let's build a model of housing. And housing, households and banks produce new households and banks, and let's model that. Or I'll give a model in a moment here. I'll describe a model of how agents and firms make more agents and firms. But we're going to discipline these models with data. So basically, the summary story here is that agent computing is a very powerful tool, but unless it's disciplined by data, we can build models of anything, and so it may be of a vague interest. Now, they could be used for theoretical purposes, but today I'm going to talk about using these models in a big data context. Okay, so here is a model of Washington, D.C. metro, the metropolitan area, and the housing bubble that unfolded there. So this is a model in which there are 2 million households, housing stock, approximately 1 million housing units that are owned, much more rented. These are one significant figure on the numbers here. Of those houses that are owned, about half of them have mortgages. And the data that we have, so we have data on roughly that entire cross-section of things, and then we also have 20 years of transactions. So the question was, how could we build a model to match what actually those households did, which houses they picked, and which mortgages they acquired to enable them to buy the house. What rules or behavior are sufficient to get a realistic bubble? Now, once again, we have the data on the transaction. We know what kind of bubble happened, and can we do this? Well, so this is joint work with, we heard from Gina Koplis yesterday, with Doan, with myself, and actually a large team of people. This work has been, we spent a couple years on this. There's more work to be done, but basically we have a model where we can reproduce the gross features of this overall phenomenon. That is the market bubble, housing market bubble in one city. But once again, the idea is that build it from the bottom up, where we have the individual households making decisions and the banks have to issue them mortgages. Another example is the U.S. private sector here. Another example of building an agent-based model grounded in data. So here now, once again, to kind of one significant figure, we have data on workers, on firms, on the networks between all these things. And in the U.S., this is about $30 trillion in output. So there's a paper and there's an upcoming book on this. But I'll go through the details here and say that today the great news is that we have the microdata. So there are 6 million firms in America, and we have data on all these things for all those 6 million. We know their sizes. We know how old they are. We know what their productivities are, growth rates, et cetera. These are data that are acquired from the U.S. Census based on tax records. Okay, from these data, and here I've just drawn the data pictorially now. We don't have time to go through them in detail. So let me just pull up a couple of them that are probably, some of them will be well known to you, some of them will not. Upper left-hand corner, there is this size distribution of American firms. There's one firm with 1 million agents There are 1 million firms with 1 agent as employees. There's an exponential distribution of ages. That's the second plot up there. Productivity on the upper part, upper line on the far right. Growth rates at the lower part, lower left. So the point is that we have these data, microscopic data on all 6 million firms in America. Can we build a model that reproduces these data? Just to give a bit more flavor for it, this is showing once again kind of one significant figure. There's 120 million workers in this in the private sector. Notice these large monthly labor flows. 2.8 million people, it says, change jobs every month to a new employer. So let's call that 3. And the flows from employed to unemployed is 2 million going each way, 1.8 million, 1.4 million. So it's another, the total flux is 3 million people. Then notice that the large flow from the employed to the out of the labor force pool, 3 million one way, 2.8 the other way. So it's easy to add this up and get more than 10 million people in flow every month. This is enormous fluctuation. This is on the order of 10% of the entire American population changing jobs every month. Now, if you have tenure at Stanford, then you characterize this as follows: rates of job separation are astonishingly high in the U.S. economy. That's one way to think about this, right? But in fact, this is the endogenous flow of workers in the economy. How do we model this in the conventional approach? We model this as if there's an exogenous shock. Shocks are hitting the economy with a hammer and causing these kinds of flows to arise. So the idea of building a model is, can we build a model where we instantiate 120 million software agents at 1-to-1 scale with the whole U.S. economy? We give them these kinds of rules of behavior, and we're going to let them move between firms when it's in their self-interest to do so. And then we let this model run long enough, there arise stationary distributions of things like team sizes, growth rates, et cetera. And then the question is, can we calibrate this model so that it looks like the empirical one? Now, there may be many ways to calibrate the model. Well, I'm going to show you one possible calibration. One calibration gives things like this. It gives that we can get skewed distributions of firm sizes. We can get exponential distribution of firm ages, and we can get the joint distribution of firms by size and by age. And then we can do other things like the growth rates coming out, productivity. I just randomly picked a bunch of things here, job tenure, et cetera. So the point is that we can today take data on the individual firms, all 6 million American firms. We can build models at full scale with the real economy. It takes heavy-duty computing to do this, but today it's feasible. And there are a variety of other areas where this kind of work is proceeding. So there's work on building fisheries management models, where we have data on every single fishing vessel, every single fishing boat, how much diesel fuel the individual fishing boats bought every day, how many fish they caught. Building climate change models in which there are spatially explicit rendering of which parts of the coastal areas will be inundated with sea level rise, et cetera. And then beyond economics proper, there are at least in Washington where I work, there are a variety of areas where these computationally intensive, data-driven models have been widely adopted by policymakers. In traffic today, 15 years ago, people did traffic as if it was computational fluid dynamics, and today people do it with agent computing. Epidemiology since 9/11 has been done with this agent-based modeling approach. And then military and combat models is the single largest area of application of agent-based computing, but with a black budget, so no one really knows how big that is. So as my time winds down here, and I'm happy to take questions as we go forward, or as we have time at the end. The conclusions are that today economics is in the middle of this kind of computational and data-rich, data-driven revolution, and that we have today the tools for moving beyond very simple, very simplistic renderings of economies. And the trouble is that if you start out with a blank sheet of paper and say, what model will I build? You can build a model of any economy, and we don't care about models of any economy. We only care about models of real economies. So today, the idea of building large-scale models disciplined with data is something that's very much possible. I've written here that in mathematical economics, it's too hard to solve most models. In agent-based models, any model can be solved. It's easy to solve any model. But the trouble is most models don't have much to do with real economy, so we need to basically hook them back to data. And then the final thing I've written here is that it's possible to make progress by trying to model real-world economies, and I think that to do that you need to have a lot of data. And it may be the case that most countries, most political jurisdictions don't have enough data gathering apparatus to do this well, have not done it well. So only in a handful of countries, Japan, a couple other places, do we have anything that looks like the amount of data we have, in this case for the US, that I've shown. But to build these kinds of modeling going forward will require us to have rich data, rich microdata, not merely aggregate data on the individual actors in the economy, the firms, and the consumers. Thank you.